Okay, so for today's lecture, we are going to start out in Chapter 2, and you're going to find that a lot of Chapter 2 is a review of concepts that you have learned in other probability courses. But what I'm going to do today is really just go over one of the examples that is presented earlier on in the textbook. The authors like to go over some definitions that you probably already know, but I just kind of delineated them here for you. I'm sure that you are familiar with the term experiment and what that means, and what a sample space is, what an event is, and certainly you've seen union, intersection, and complement of sample spaces. So I'm going to be using, all of these terms here in the next example that the authors present. Now, what you don't know is prior to this particular video, I had started to do the next slide, and then I said something wrong, so I had to start all over again, which makes me quite angry. So what you're going to see here is some notation that I had started. So let me explain what we're doing. We're going to cut a 1 meter stick, okay? We're going to cut a 1 meter stick in two places and see if we can form a triangle from it. And that's the whole purpose of this problem, is to determine the probability that we can form a triangle from the three resulting pieces. So we are going to define event A here as the event that we can make a triangle, and then we're going to define the event. We are going to define the event 1 and event 2 as two different ways that a triangle can be formed. And the other thing, and I remember when I first taught this problem, I had not remembered this, I guess, from, I don't know, junior high or whatever, but in order to be able to make a triangle from three pieces, all of those pieces has to be less than, well, in this case, less than a half a meter, or a half of the length of the stick that you're cutting. So here we have event 1. Now what is event 1? Event 1 is the case where I make my first cut, let's say x1, but my second cut is to the left of x1. So therefore the length of my three pieces for event 1 will be, this piece is going to have a length of x2, the middle piece will have a length of x1 minus x2, and then the third piece, which I'm going to be color coding in green, by the way, this piece will be the 1 meter minus x1, and all three of those pieces has to be less than a half. I can do the same thing. I have another situation, which is event 2, and that says I make my first cut, which is x1, but in this case my second cut is actually to the right of my first cut, and so in that case I will have my three pieces as x1 will be this piece, which has to be less than a half a meter. x2 minus x1 has to be less than a half a meter. And then finally that last piece, 1 minus x2, has to be less than a half a meter. What I'm not color coding these because I'm going to draw event 1, and then I'm going to let you figure out where event 2, how event 2 works, or graphs, or maybe I'll graph it and you can just verify it. How's that? Okay, so what I want to do here is plot each of these regions. So the first region, if I'm going to start with event 1. So the first region says that x2 has to be less than a half a meter. So that would be represented by this orange line and then all of the area below it. If I wanted to plot the, well, let's do the easier one next. If I do the green one, which is 1 minus x1 has to be less than a half, that's the same thing as me saying that x1 has to be bigger than 1/2. So that would be represented here. Oh, it's not the straightest line I ever made. So this line right here, or region I should say, is 1 minus x1 is less than a half, and you can rearrange those terms to see that that says that x1 has to be bigger than a half. And then this middle piece here, if for example right here, if I were to set x2 equal to 0, then x1 would be at a half, and if I were to set x1 equal to 1, then x2 would be at a half. So anyways, the point is I can plot this as a line as well, and that is going to look something like this. The question is, which way will the arrows go? So this is the equality form of x1 minus x2 less than a half. And if you just plug in if you just plugged in 0, 0, you would be able to see that the arrows for this region have to go this way. And therefore, my sample space for event 1 is going to be the intersection of all of these three color-coded regions right here. And that ends up being, and I'll just kind of shade it right here like this. So we could call this the sample space that is event 1. What you'd be able to do if you wanted to is you would also be able to show, if you were to plot these three, and I encourage you to do that, and I won't use color code here, but what you'll find is you will end up with a region, and I'll have you verify this. So as you're going over your notes, or stop the video right now and show that this is the region for all of the points that would comprise event 2. And so now we're in a very good position just using geometry here to determine what the probability is that we can create a triangle. So the probability we can create a triangle is just going to be the probability that we have event 1 or event 2, and just by using 1/2 base times height, you can see that if this is a right triangle here, right, 1/2 the base, which is 1/2, times the height, which is 1/2, so that's 1/8, and then we also have the probability of event 2 is also the same. And so the probability that we can make a triangle by doing 2 random cuts of a stick of 1 meter ends up being 1/4. I just like this problem because it kind of gets your feet a little bit wet with the course. Okay, next slide. Just a little bit of a review here. If we wanted to find the union of 2 different events, A and B, we can express that as the probability of A plus the probability of B minus the intersection. Many of you have learned this as something called the addition rule. Then we can also look at conditional probabilities here. The probability of A given B, well, we can look at that as the probability of the intersection divided by B, or we could also write it this way, and I don't know why my B and my A are so big there, but you probably recognize this as Bayes' theorem. And obviously the probability of B has to be something bigger than 0. And then another conditional probability that we're going to be using is the probability of event C given A is just going to be the probability of C divided by the probability of A, which is kind of what we just did really with the geometric probability, because we had a 1 meter squared total sample space. In fact, I'm thinking I might want to go back here. Let me just go back. I didn't really identify that. This whole square here would just be my total sample space, because x1 can be between 0 and 1 and x2 can be between 0 and 1. Sorry for backing up like that. This is probably a good time for me to pause and tell you, I taught this course for a number of years, and then I didn't teach it for a while. They kind of shuffle us around as faculty members, and for a while Dr. Safar was teaching this course. And so I haven't taught this course since 2015, so I'm a little bit rusty. So sometimes I have these afterthoughts, so please be patient with me. Finally, if A and B are independent, then we have these relationships, that they're intersection of A and B. If they're independent, we just multiply those probabilities, and the conditional probability of A given B is just the probability of A. All right. Last slide of this very short lecture. They're not always going to be this short. Random variables, something you need to know about me. I have terrible handwriting, but you probably figured that out already, right? I like to denote my random variables because they're always capital letters, but you're going to find that because I want to make sure you understand that I'm talking about random variables, I will always put a line underneath a letter that I am trying to designate as or that I am designating as a random variable because it indicates that it is a capital letter. Whenever we have lowercase letters, lowercase x, y, t, and z as examples, these are going to indicate that we're talking about a very specific value, numerical value of the random variable. So just be aware that when you see me underline, you don't have to take your notes that way. It's just me because I want to make sure you know I'm talking about a random variable. So this is kind of an important point. It's the way I teach my other undergraduate probability courses, and some of you have had me as a teacher before and have seen this, so I just want to be clear. So this is as far as I wanted to go with this short little lecture. I'm trying to compartmentalize the slides. Chapter 2 is very, very long. So I will see you for slides, what's this? This is slide number 5, 6 through something on the next recording.